You're scrubbing a yellow curry stain on a white shirt. Instead of fading, the spot reacts to the soap, blooming into a deep, vibrant red. This shift happens because turmeric, the primary spice in curry, functions as a natural indicator. It undergoes a physical color change the moment it encounters the basic ingredients found in most soaps. At a molecular level, these changes are driven by the presence of hydrogen or hydroxide ions. Acids are substances that release H+ ions, while bases release OH- ions. This flowchart shows how we identify these invisible particles. We use natural indicators like turmeric, lab-synthesized chemicals like methyl orange, or olfactory indicators that signal a chemical shift through a change in smell. Beyond chemical tests, these substances often reveal themselves through physical traits. Acids typically have a sharp, sour taste, while bases are bitter and feel uniquely slippery or soapy to the touch. To identify them safely in a lab, we often turn to litmus. It's one of the oldest natural indicators in use, originally extracted from a type of plant called lichen. Litmus follows a predictable set of rules. Blue paper turns red when dipped into an acid, and red paper turns blue when it encounters a base. While these tests tell us what a substance is, the true impact of these chemicals becomes visible when they begin reacting with the physical materials around us. This chart is the pH scale, the universal tool used to measure the concentration of those ions. It ranges from 0 to 14, with 7 representing a neutral midpoint like pure water. Moving toward the lower end of the scale increases the acidity, and at these concentrations, the chemicals become aggressive enough to attack solid metal. When solid zinc granules are submerged in dilute hydrochloric acid, they break down, creating a violent stream of gas bubbles. Igniting a soap bubble filled with this gas produces a sharp pop, confirming it is pure hydrogen. Acids have the capacity to dissolve solids and release volatile gases, making precise measurement on the pH scale a matter of safety and control. Since acids and bases are both chemically aggressive, a unique reaction occurs when they are mixed. This is called neutralization. The H+ ions from the acid and the OH- ions from the base collide and bond, effectively canceling out each other's reactive properties. As the ions pair up, the dangerous chemical extremes vanish. They leave behind only 2 neutral, harmless byproducts, ordinary salt and water. By pitting these opposites against each other, we neutralize hazardous substances and achieve total chemical equilibrium. This isn't just a laboratory phenomenon. Our own bodies are built on a fragile pH balance that requires constant maintenance. Your tooth enamel is the hardest substance in your body, but it's vulnerable to pH shifts. If the environment in your mouth drops below 5.5, the acidity begins to dissolve the enamel structure. Further down, your stomach uses highly concentrated acid to digest food, but an overproduction of that acid leads to the burning sensation of indigestion. To fix this, you swallow an antacid, a mild base. It triggers a neutralization reaction inside the stomach, turning the excess acid into salt and water. Every single day, our biology performs this chemical balancing act, using bases to mitigate the damage caused by acidic extremes. We see the same mechanics on a global scale. Industrial emissions release compounds into the atmosphere that eventually return to Earth as acid rain. When rain hits a pH lower than 5.6, it begins to alter the chemistry of our rivers and soil, pushing them away from their natural neutral state. These chemical shifts have biological consequences. Sensitive aquatic life cannot survive in acidic water, and forests begin to die as soil pH moves outside the range required for healthy growth. These invisible ions dictate whether a river can support life or if a landscape remains fertile enough to grow food. Understanding these rules allows us to monitor environmental health. By measuring pH shifts and applying the principles of neutralization, we can manage industrial runoff and stabilize the chemical balance that the natural world depends on.